All right then, so let's move on to looking at modelling pitch moment. So again, we return to our definition of the stability axis system, and again refer to figure 3.3 from the textbook. So here we can see how our forces and moments relate to the new definition of the stability axis system, and we can see that our pitch moment, steady state pitch moment, due to aerodynamic forces is ma1, and that's going to be equal to m1 for our trim condition, where m1 is equal to the pitch moment coefficient at the trim condition multiplied by the dynamic pressure multiplied by the wing reference area multiplied by the mean aerodynamic chord. So this is the different part now, because we're going to use the mean aerodynamic chord to non-dimensionalize the moment arms, which are going to be associated with the aerodynamic forces causing our moment about the center of gravity position. And we can see that if we return to the textbook and look at figure 3.9, you can see the distances between the aerodynamic centers of the wing and body and the horizontal tail, for example, have been non-dimensionalized using the mean aerodynamic chord C bar. And once they've been non-dimensionalized, they're given this notation with the bar notation. Okay, so as we looked at before for the drag and lift forces, at a particular Reynolds number, this is similar to what you've just seen, at a particular Mach and Reynolds number, this pitch moment coefficient is a function of angle of attack, elevator deflection angle, and the incidence angle of the horizontal tail. So again, we can apply a Taylor series expansion about the reference condition, this one here, to get this. So obviously pitch moment coefficient at the trim condition, and then the derivatives, the pitch moment stability derivatives with respect to angle of attack, with respect to elevator deflection angle, and with respect to inclination angle of the horizontal tail. So now we just need to think about, geometrically speaking, which forces contribute to the overall pitching moment of the aircraft. So for example here, I've tried to depict the lift and drag forces of the wing and body combined, so L subscript wing body and drag subscript wing body, right, to try to depict where those forces act in relation to the center of gravity position. So on here I've got the original body axis, x-axis, drawn, and the new stability x-axis, which is going to be our direction of flight, right? So remember that this is this, but converted for angle of attack, right? So it's adjusted for angle of attack. So xs is going to be our direction of flight, or the direction of the free stream velocity, right? So that gives us two things. That gives us the moment arm associated with the lift force, and also the moment arm associated with the drag force, because if we have the aerodynamic center of the wing and body, we know that's where our lift and drag forces are acting. Okay, so if we know that this is the point where our lift and drag forces are acting from, we have this distance here, which is just the x distance between the aerodynamic center of the wing and body and the center of gravity position. So what we're left with is just a little bit of trigonometry here to work out where these moment arms associated with that lift force, which is perpendicular to the x stability axis, and this drag force, which is parallel to the x stability axis. So I'm just going to do a little bit of trigonometry on this little right-angled triangle in here. So I'm calling this length here little x1, and that's going to be the moment arm associated with the lift force, right? So a moment is a force multiplied by a perpendicular distance, so this is going to be my perpendicular distance for this force. So doing a little bit of trigonometry on that, cosine of the angle of attack is going to be that moment arm divided by what's essentially our hypotenuse, which is the difference between the aerodynamic center of the wing and body combined and the center of gravity position. So I get this. just rearranging that, right? And I can do the same for this moment arm, which is going to be the moment arm associated with the drag force, so that's acting at a perpendicular distance x2, right? So again, I end up with this expression here. So that just shows you how we work out the moment arms associated with the aerodynamic forces of the wing. Obviously, we'd have to repeat that process to find the moment arms associated with the lift and drag forces on the horizontal tail. But essentially, if we did that and repeated it, we would get this expression here. So the moment, the overall moment, is the moment about the aerodynamic center of the wing and body in the trim condition, plus the force times the moment arms of all of these forces, right? So we have a lift force with its associated moment arm, we have a drag force with its associated moment arm, and those two are for the wing and body combined, and then we have these two associated with the horizontal tail. So notice how these ones are positive because the aerodynamic center of the wing and body combined is ahead of the center of gravity position, and these ones are negative because the aerodynamic center of the horizontal tail is rearwards from the center of gravity position, which means that we have our moments acting in opposite directions, right? So, and also recall that the angle of attack on the horizontal tail is the angle of attack affected by downwash. So now if we go ahead and assume, like we did in the formulation of the perturbed flight conditions, that if we're only interested in a small perturbation about that trim condition, we can make these small angle approximations here as we did in the formulation of the perturbed flight conditions. We also assume that the lift due to the wing and body combined is much greater than the drag. That's a reasonable assumption to make. And we also assume that the drag due to the horizontal tail is negligible. So what happens is we can reduce down this equation down here, which we just found, using those assumptions to get this neater looking thing right here. And then we can rewrite that in terms of our coefficients like we did up here with M1, for example. What we do is exactly the same thing. We break this down into coefficients. We multiply by the dynamic pressure, wing reference area, and the mean aerodynamic chord in all cases. And what that allows us to do is use some things that we found in the previous couple of sections when modeling the lift coefficient. So recall that from the previous video, the lift coefficient due to the wing and body can be written as this, and the lift coefficient associated with the horizontal tail can be written as this. So recall the previous video where I'm modeling the lift forces for those two expressions. So what happens if I put all of that together is I get a slightly bigger mess, but then I can take these terms from the left hand side, divide through by Q bar S C bar, and also make the same assumption as in the previous section that the lift coefficient due to angle of attack on the wing and body is approximately the lift coefficient due to angle of attack of the wing. So we're assuming that the body contribution is negligible basically. So by assuming that, dividing through the whole right hand side by Q bar S C bar, I get an expression for CM1. Then the last thing we need to do with this equation, as I mentioned at the very start of this video, is non-dimensionalize these distances with respect to the mean aerodynamic chord. And these are the expressions used on that figure in the textbook, right? Figure 3.9. So they're just these ones. So we use those expressions to non-dimensionalize with respect to the mean aerodynamic chord. We put all of that back into our equation to get this. And then what we do is compare this equation that we've just derived with our original Taylor expansion equation, this one up here, which I called star, and then I can start comparing each term of my new equations to the terms which multiply alpha, delta sub E and I sub H. So you've seen something similar to this in the previous couple of sections. So I take this equation, and so I find all of my terms that are not multiplied by either alpha, delta sub E or I sub H. They become my Cm sub 0 terms. So this term, as I've written here, this term describes the capability of the wing and body to provide a nose up pitching moment, so that's for stability, at angle of attack equals 0. Then to get Cm alpha, I just compare all of the terms of this equation which multiply by alpha, right? And so on and so on. So I do the same for delta sub E, find all the terms of this equation which are multiplied by delta sub E, and then compare them to this equation, and so on and so forth. And then I get 4 equations, the fourth of which I can use to rewrite the third. So notice that negative Cl alpha H multiplied by this difference here, that obviously should have a bar, multiplied by the ratio of dynamic pressures and the ratio of reference areas. That can be used to simplify this because all of those terms appear in this, apart from the tau sub E term. So that's the final set of equations for the pitch moment derivatives.